So this is truly a time crystal that is macroscopic, and it's something we can see.
We have an ocarina of time.
Yes.
Physicists at the University of Colorado Boulder have created the first time crystal that humans can actually see using liquid crystals that swirl into a never-ending pattern when illuminated by light. They put out their paper in Nature Materials.
The laws of physics are symmetric to space translations, right? Well, similarly, the laws of the universe are also symmetric in time. Right? So if we have things that break spatial symmetry by creating crystals in space, right, where you have clearly like carbon making the diamond or NaCl making table salt, so you clearly have spatial crystals. What if I have a breaking of the time symmetry to create a time crystal? And what would that look like? What that would look like is you've got some kind of periodic system that returns to its original form periodically. And there were specialized quantum systems that could do this, right? There were nuclear spins, trapped ions, cold atoms at extremely low temperatures, quantum weirdness. This paper is very cool because it's doing it in a classical system, which means no quantum weirdness, and it's doing it at room temperature.
Wow.
And it's doing it at a big enough scale that we can see with our naked eye. So they figured what I can do is I can create a liquid crystal, and when it's shined on by light, what you're going to get is deformations in the crystal.
Yes.
Okay? Tiny little deformations in this lattice. So they're all oriented in one direction, but I've taken like a tiny little neighborhood and I've like bent them in a certain way. Okay? Such that that bend, which becomes this sort of topological defect, that twist can then influence the stuff around it, which can influence the stuff around it, which can influence the stuff around it. And what you get is this sort of traveling wave of disturbance. Okay? They're what are called topological solitons in physics. This idea that like a disturbance kind of acts like a particle. Okay? Because it travels the same way as a particle. The orientation of that disturbance can have a charge, in the sense that if I twist it clockwise, then it's a plus one. And if I twist it counterclockwise, it's a minus one. And that charge is conserved in the same way they can cancel each other out, kind of the same way that... And all of these deformations act like little quasi-particles that interact with each other and have a physics to themselves that is an emergent property of the little tiny rods themselves.
That initial disturbance that has now created a cascade. That is now independent of the initial source.
This is not a property of the outside drive. It's a property of the material itself.